Okay, in our last lesson, we were looking at the derivative of a specific exponential function that had a base number of e, which we said is a special number in math. Today what we're going to look at is taking the derivative of an exponential, but now the base number can be any number. So we're going to try to investigate this to see if we can come up with what the derivative is. So the first part of today's lesson is an investigation, and it's not something that you would be asked to repeat on the test. It's just like, where does this come from? So we need to introduce something called the natural logarithm. Remember that e was called the natural number. So the natural logarithm has the base number e. So it's log base e of some number a. And we short form that, since it's the natural logarithm, we just say it's ln of a. So whenever we see ln of a, it means log base e. You have a button on your calculator for ln. That's how special this is. So hopefully you can find that number on there. If you type in ln e, you should get one. You should have an e button on your calculator as well. See if you can find that, but you want to get used to using those buttons. In our investigation, we're going to use log laws. Now, remember that if I have, from yesterday, if I have e, this is ln 2 in the exponent, but remember ln means log base e. So this is e to the log base e of 2, right? I'm just replacing the ln with log base e. And remember from yesterday, or maybe it was 2 days ago, we reviewed our exponential rules that if I have e raised to the log base e of something, that's just equal to the something. So it's kind of like these two cancel away, and I bring the 2 down. So when I have e to the ln 2, that's just 2. So what I'm going to do is replace, I'm going to investigate 2 to the power of x. I'm going to see if I can figure out what the derivative is for 2 to the power of x. So instead of writing 2, I'm going to replace, I know that 2 is the same as e to the ln 2. So I'm going to fill that in here. I've just replaced the 2. The x is still there as the exponent on this. So I can simplify this another way to write this. I don't need to put the brackets around the base. I can put in the exponent, it's ln 2 times x. Now, it's hard to tell what I'm taking the ln of when I write this. So we have to be specific. Like, are you taking ln of 2 times x? Or are you taking ln of 2 and then multiplying by x? So we are going to put the brackets there around the ln 2 to show that I'm taking the ln of the 2, whatever that number is, I'll multiply it by x. All right, so we can find the derivative then of y equals 2x. Y equals 2x, we just said 2x is the same as e to the ln 2 times x. And then I can take the derivative of this, because from yesterday I know how to take the derivative of a base e exponential. So then I can say that y prime is equal to, when I take the derivative of a base e exponential, I just write it down exactly how it was. Oops, ln 2. And then I multiply by the derivative of the exponent. Now remember, ln 2 is just a number. It's a decimal number. So I've got some decimal times x, and when I take the derivative of that, it's just the decimal number, so it's just the ln 2. And so I've got kind of a messy expression here. We're going to see if we can simplify this so that we can come up with like a trick for taking the derivative of 2 to the power of x. So what I'm going to do here is sub back in that e to the ln 2 is equal to 2. So I'm just replacing this part here. So this is really 2, and then the x is still there in the exponent times ln 2. And so normally we rearrange this and we would write the x at the back. We always take our numeric coefficients to the front. And so here I've got ln 2 times 2 to the power of x. Now be careful here, the x only goes with the 2. There is no exponent on ln 2. It's kind of like when I see people do this sometimes. If I had 3 times 2 to the x, this does not simplify as 6 to the x because the 3 has no exponent, so I can't just combine them. So just watch out for that. All right, so we've come up with the derivative for y equals 2x. 2 to the x, sorry. I want to now try to figure out, well, what would happen if I had y equals 3 to the x? And you can kind of go through this whole process again. If I had a 3, if I had a 3 up here in the exponent, then I would get a 3 down here. So if I had 3 to the x, everything would be the same except there would be a 3 in here. And you can track this all the way through. It's going to be all the same except all the 2's will change into 3's. And similarly, you could do it for 4 to the x, then these 3's would change into 4's. And this is how we come up with our rule for finding the derivative of an exponential function. If my function is some number b to the power of x, then the derivative is going to be ln of that base number times b to the x. Okay, so I still have the original, kind of like before with the exponential, but this time I have this extra ln b in front. Now, what happens if there's a function up in the exponent instead of just an x? So maybe the exponent, like maybe it's some number, like it's some number b, and then there's like a 2x plus 1 up in the exponent. How would I take the derivative of this? Well, first I would take ln of the base, and then I would write down the original function exactly how it is, and then I'll multiply by the derivative of the exponent. So I'm going to have ln of the base times the original times the derivative of the exponent. And this is just chain rule, right? In this case, the outer function is the exponential, and then the inner function is the linear in the exponent here. So I take the derivative of that at the end. All right. Let's try some examples. So we're going to differentiate. We've got g at x is equal to 8 to the power of x. So this is a nice simple one because there's nothing really going on in the exponent. So taking the derivative, I take ln of the base times the original. And then I would take the derivative of the exponent, but again, the exponent is just x. So I'm all done here. For communication, I do want the x's at the end when you have a bunch of things multiplied together, numeric coefficients at the front, and pieces with x's at the back. It's kind of like you wouldn't write x times 3, right? You would rearrange that and write 3x. All right, our next example here, I've got h of x is equal to 5, and this time we've got some stuff going on in the exponent. So when I take the derivative, I take ln of the base times the original, and now I'm going to take the derivative of the exponent. So now just looking at the exponent, bring the 3 down, I get 12x squared minus 1. Now I am multiplying these 3 pieces all together. So there are, because this last piece involves a subtraction, it is necessary to put these brackets in here. And then the last thing I would check is if I have 3 things being multiplied, do I have this, the pieces with no x's at the front, because those would be coefficients. So ln 5 has no x in it, it needs to be at the front. These two both have x's, and so we can say that the order here will be interchangeable for this year. All right. In example 2, when does f at x, we've got a root with an exponential over a linear, and I want to know when does this thing have a horizontal tangent. So remember, when we're looking for horizontal tangents, we're looking for when does the derivative equal 0. All right, so the first thing I'm going to do is rewrite this equation instead of writing it with a root. I know that the type of root becomes the denominator in the exponent, so this is a square root. So the denominator is 2 in the exponent, and then the x will just tag along as the numerator. All right, so making it clear when you write what's up in the exponent and what's not. So this x is down on the same baseline as the 3. This is just a communication piece. Sometimes it's hard for me to read your work. And the x over 2, there should definitely be a space here before I get to the bottom of the 4 so that I can tell that that's in your exponent. All right, we're going to take the derivative because we want to figure out where does it equal to 0. So I've got a quotient rule here. So I'm thinking about, I've got like a u on top and a v on the bottom. So I'm thinking through my quotient rule. So taking the derivative of the top, we've got an exponential with base 4. So I take ln of the base times the original times the derivative of the exponent. Now another way to write x over 2, so you can also be thinking about x over 2 is the same as 1/2 times x. So when I take the derivative of that, it's just 1/2. All right, so that's u prime. That's all we've done so far. Now we need to multiply by v. And then we'll subtract. Now we're going to leave the numerator alone and multiply by the derivative of the denominator. So this one's a little simpler. And then in the denominator, we're going to square the old denominator. All right, so we're going to try and clean this up. In the numerator here, it splits at this subtraction sign, right? So I have one term out front and then a second term here. I'm looking for what do they have in common. So I notice that they both have a coefficient of 3 that I can pull out, and they both have the exponential 4 to the power of x over 2. So I can pull that all out. I'm going to change the order so that the 3 is in front since it's numeric. Oops. And then we'll open up a set of brackets and figure out, well, what's left over here. So I've got the 1/2 times ln 4. So these are both numeric coefficients, and you could put them together in one fraction as ln 4 over 2. That would work as well. And then there's the x. Again, I need to be clear here that I'm just taking ln of 4, not the ln of 4 times x. So I'm going to put a dot in, or I could use brackets to separate them. And then in the second term here, we actually divided out the exact second term, so I'm left with subtracting 1. And then that's all over. Be careful here, when you square the denominator, you are squaring the 3 and squaring the x. All right. So I want to know, where does this thing equal 0? I do have a common factor here of a 3, so you can cancel that away, and I'd be left with 3 down here. And then I'm going to bring the 3x squared up and multiply it on the other side, and I'm left with just 0 equals the numerator. Oops, on 4 times x minus 1. Right, so I did take that denominator up and multiply it by 0 on the other side. All right, so we want to solve this. I've got it already factored, which is nice. So if I have two factors being multiplied to equal 0, either the first factor equals 0 or the second factor equals 0. All right, so we're going to reason our way through these. For this first one here, I'm going to go through two possible things that you could write down. You would not write down both of them. When I look at this first one here, I can tell that there are no solutions. And I can either think this through algebraically, or you can describe a graph or draw a quick sketch of a graph for me as well. So I'll do the graphing one first. And again, you would be either giving me the first explanation, or I'll do a second explanation off to the side. You're not going to write both. So the first thing I can do is say that I recognize that 4 to the power of x over 2 is an exponential graph. Right, I've got the base number 4, and then in the numerator, in the exponent, I have a multiplier of 1/2. So that's my k value. It tells me that there's actually a horizontal stretch by a factor of 2. So I know that this graph looks like my regular exponential. Hopefully you remember what this looks like. There's my exponential graph, and it's been stretched out horizontally by a factor of 2. Even with a horizontal stretch, though, this thing has no x-intercepts. And that's what this equation was looking for, right? When does the graph of this have a height of 0? And it never has a height of 0. So that's one way for me to explain it. If you don't like the graphical explanation and you prefer more of an algebraic approach, then I can rearrange this, thinking back to our lesson 5.0 where we reviewed how to rearrange this and write it as a logarithm. And so if I want to rewrite this as a log, the base on the log is the base of the exponent, and the log is going to be equal to the exponent. And then I'm going to take log base 4 of 0, right? That was our power. Now, when I try and type log base 4 of 0 into my calculator, I'm going to get an error, and that's because log base 4 of 0 is undefined. It's saying what's the exponent on 4 that gives you the answer 0, and it's never going to happen, right? Because no matter how negative I make that exponent on 4, it's just going to be a fraction that gets closer to 0 and never actually gets there. So log base 4 of 0 is undefined, and therefore I have no solutions. So again, you're going to write down one of these two explanations to tell me why there are no answers to this one. This guy, though, we still need to solve. So I'm going to rearrange this. I've just kind of run out of room here. I wonder if I can drag it. Yeah. Okay, so we need to rearrange this, and I want to solve for x. Now, I need to remember that this piece here is just a coefficient, right? It's a multiplier in front of x, and it's a decimal multiplier, but it is still a coefficient. So you can think about this equation as some number, some coefficient times x minus 1 equals 0, and ask yourself, well, how would I solve that? Well, what I would do is I would move the 1 over and then divide out the coefficient. So I'm going to move the 1 over, it becomes positive 1, and then I'm going to divide out the coefficient. So hold on here, we'll take our time here and step this out. You can move them over one at a time if you like. I'll take the 1/2 over to the other side. So if I'm dividing by 2 on this side, I'm going to multiply by 2 on the other side. And then I've got the ln 4, so I'm going to divide it out to the other side. Or you could do that in the opposite order. You could move the ln 4 first and then the 2. Either way, you're going to come up with this answer here that x is equal to 2 over ln 4. And that is our only spot where we have a horizontal tangent. That's what the question was asking for. Therefore, all right, they didn't ask me for the point. They just asked me when does it have a horizontal tangent, so I'm not going to find the y value, and I'm all done with that question. All right, enjoy your homework.